All right, here's the final free response question for BC Practice Test 3. This is question 6, and it's involving some information about a Taylor polynomial that's used to approximate this function f about a center at x equals 1. All right, so now it says find f triple prime of 3 in part A. Well, the third derivative should go with the third degree term in your Taylor polynomial. So identify where the third degree term is. That's going to be that 5 times x minus 1 to the third power. And if you remember how you set up a Taylor polynomial, right, the number of the derivative of the original function that you're approximating, that same number matches the degree of x in that term and the factorial underneath that. So that 5 coefficient over there really is f triple prime of 1, that 5 right there, over 3 factorial. So f triple prime of 1 is going to be simply 5 times 3 factorial. 3 factorial is 6, so 5 times 6 is equal to 30. There's no real wording of the question to write a sentence here, so that's about it. Now on to part B. Does the graph of f have a relative minimum, relative maximum, or neither at x equals 1? Well, I don't really have the function rule for f, and I don't really know what its specific derivatives are other than I know what the derivatives are at x equals 1. So instead of doing a first derivative and finding critical numbers and doing a sign chart and seeing if the first derivative changes sign, since I don't have a derivative rule for the first derivative, I'm going to use the second derivative test because all of these coefficients of my terms in my Taylor polynomial come from the derivatives. Right? So, since there's no x minus 1 to the first power term, the only way that x minus 1 to the first power could have been eliminated is if f prime of 1, the first derivative of 1, was equal to 0. That would have canceled out that term. Now, that's a jump to make logically, I get it, but once you can see that that x minus 1 isn't there, the first derivative has to be 0, and if the first derivative at 1 is 0, that's telling you that x equals 1 is a critical number. All right? Now, if I go to the second degree term, I can figure out what f double prime at 1 is equal to. Now, that's the way the second derivative test works. You find your critical numbers and then you substitute them into the second derivative. Now, I know that x equals 1 is a critical number because f prime of 1 had to be 0. So now I'm going to figure out what the second derivative at 1 is by going to the second degree term. And that is that negative 6 times x minus 1 to the second power. Well, just like we did in part A, I'm going to set that coefficient equal to f double prime of 1 over 2 factorial. Multiply both sides by 2 factorial, which is just 2, and I get negative 12. Now, I'll write this out in a moment, but just keep in mind, my second derivative at a critical number is negative. That meant that the parent function f has to be concave down, which means you have a relative maximum there. So let's put it into words. Since the second derivative is negative at a critical number, again, let's kind of highlight that out. Second derivative is that f double prime of 1 there. That's negative at a critical number. The critical number came from the fact that f prime of 1 was equal to 0. F has a relative maximum at x equals 1. You can say by the second derivative test if you want to, but this is more than enough to get you credit for that. All right, on to part C. Now, g is this new function, and g is the antiderivative of f. They're writing it out as an integral like that. Now, our Taylor polynomial approximates f. So if you want to use the Taylor polynomial to approximate g, and g is the antiderivative of f, you have to antidifferentiate your terms for the Taylor polynomial. Now, it's easier than you think, and they make it even easier still in this part C because they only want the third degree Taylor polynomial for g. Now, when you antidifferentiate powers of x, you add 1 to your exponent. So to wind up with a third degree Taylor polynomial, I only need to go up to the second degree term when I write this out. Right? I only need to anti-differentiate here the first two terms. So I'm going to write out capital G for my third degree Taylor polynomial used to approximate lowercase g of x. And that is the antiderivative from 1 to x. Instead of f of t, I'm going to replace f of t with the first two terms of the Taylor polynomial for f. And when I anti-differentiate that, right, that constant of 3 is going to get a variable put next to it. That's going to be the t minus 1. And the t minus 1 to the second power, add 1 to the exponent and divide by the new exponent, so that negative 6 will become negative 2. Now I'm going to evaluate this expression at the upper limit of x minus this expression evaluated at 1. But I hope you can see at 1, all the t minus 1s are going to become 0. The whole thing's going to drop out. So I really just need the upper limit of integration. So that's 3 times x minus 1 minus 2 times x minus 1 to the third power. That gives me my third degree Taylor polynomial to approximate this. I do want to make one point here. This capital G sub 3 of x, if you write that in, you don't need to say the third degree Taylor polynomial. That will let the people grading your paper know that that's the case. All right, we have to use it to approximate g, lowercase g, the actual function of 1.1. So g of 1.1 is going to be approximately equal to this third degree Taylor polynomial at x equals 1.1. Again, you're not allowed to use a calculator, but if you do 1.1 minus 1, you get 1/10. And 1/10 is easy to work with. All right, so you wind up with 0.298 as your approximation. Okay, now that was anti-differentiating the Taylor polynomial they give you. In part D, you can see now it's a new function, h of x, which is equal to the derivative of f. And now we're going to use the Taylor polynomial they gave us for f, and we're going to differentiate each of those terms to get an approximation, a third degree approximation for h. So we're just going in the other direction now. Now, because they want a third degree Taylor polynomial for the derivative of f, right, I need all of my terms here right up to the fourth degree term, because when I differentiate that, I'll wind up with a third degree term. So I'm going to differentiate the original one. The original one is there, the 3 minus 6 times x minus 1 squared, and so on and so on. And now I do this capital H. This is my third degree Taylor polynomial to represent the actual function h of x, lowercase h of x. So if I anti-differentiate each of my terms here, right, we'll go one at a time here. This is going to become this. Sorry, my highlighting is a little off here. This second term, when I anti-differentiate, will become this. And finally, the third term there will become that. All right. Now, I have that third degree Taylor polynomial from the derivative. That's fairly easy to do. I have to verify that the graph of h does not have a point of inflection at x equals 1. Well, to have a point of inflection at x equals 1, at the very least, your second derivative has to be equal to 0, because your second derivative has to change sign. So my second derivative is going to come from the coefficient of the second degree term. So I'm looking at that blue highlighted term, 15 times x minus 1 squared, right? All of the derivatives of this polynomial are the derivatives of h. So that 15 is going to be h double prime of 1 divided by 2 factorial. And if I multiply both sides by 2 factorial, I get h double prime of 1 equals 30, which means that my second derivative at x equals 1 is not equal to 0. So I'm going to go above in the white space there and write my answer sentence. Since h double prime of 1 is not 0, the graph of h does not have a point of inflection at x equals 1. And that is the end of part 6. I hope this helps. Whatever questions you have, just let me know in class.